So, my name is Steve Purves. I'm ffA's Technical Director, and I'm going to talk today about how GPU computing is changing our software, it's changing the way that we are designing our software for the oil and gas industry. Specifically, there's an area of seismic interpretation which will really benefit from using the GPU for computation on the desktop. And seismic data is effectively an acoustic image of the Earth's subsurface. A lot of it is taken offshore, so a lot of it is marine. So what happens is we have an acquisition boat that basically makes loops up and down over a few hundred square kilometers of the sea. There's a sound source that sends out shots, and there's a set of hydrophones on streamers that record the reflection. So we record reflection strength, the actual geometry, and the travel times. And from that, we're able to build up an accurate image of the Earth's subsurface. So this is what seismic data looks like. So on the left, we have some geology. On the right, some seismic data. So if you have a look in here, we've got this sort of bright red reflection. So that signifies an impedance change, a change in acoustic impedance. So let's say red is a step up, and then blue is a step down. So these impedance changes and these reflections actually correspond to changes between different rock types in the subsurface. We've also got a lot of faulting in here, where the rock's been disrupted, and you can see faulting come through in the image quite well as discontinuities. So the purpose of seismic imaging is to image the structure. The purpose of seismic interpretation is to go back and try and understand the geology, which is something which is done manually, and it's something which is actually very difficult to do. Of course, the world's 3D also. So we actually analyze 3D volume of seismic data, which for an interpreter, for a human who can easily understand 2D, understanding 3D, even with visualization environments today, is a big challenge. So we can bring computation into play there to help them do that. So every oil and gas company who operates today has a workflow which goes from acquiring seismic data, usually terabytes of data at this stage, then processing that raw data into a consistent 3D image of the Earth, a process that takes months or up to a year. Then you have seismic interpretation, which is the area we deal with. And like I say, teams of geophysicists work interpreting this data, usually manually, by clicking and picking and drawing lines, in order to build up something like this, which is a detailed geological model. 15 years ago, you would have seen people with massive printouts of this on the wall. These are individual seismic responses, so the individual wiggle traces. And people would come along and begin looking at these and trying to draw geology on top of them. Today, you still find some people doing this, but thankfully they're using computers to do that. So the industry has come forward though, and it makes big use of 3D visualization. So now there are 3D visualization tools that allow you to look at seismic in this way, and it allows geophysicists to pick and define these surfaces, so faults and event horizons, more rapidly than that one before, and they're able to consider it as a 3D object, which is good. But it is still a very manual and subjective process, and one that takes a long time. So an initial seismic interpretation using modern manual tools will still take 3 to 6 months. Just by stepping away from manual and taking a computational approach, you can take building of that model from 6 months down to a matter of a few weeks. And these detailed images also reduce risk, which is a key factor. As if you're going to make a drilling decision that's going to cost $100 million, you want to make exactly sure that everything is where you think it is. This is an example of what we do. So we do data conditioning in order to clean up the seismic. And then we do a range of analysis to look at geological structure, to look at frequency properties, to image and separate out and segment faults. And actually stratigraphic imaging, which essentially is producing detailed bodies, structures that relate directly to oil and gas deposits. We then produce these hybrid data volumes, which can be gigabytes in size, that geologists uses. This is the starting point for their interpretation, and they can go from that to their model much more rapidly. Our algorithms already are computationally intensive, and they're going to be more computationally intensive. We're dealing with increasingly large data volumes, A couple of years ago, 3 or 4 gigabyte would have been a big data volume for us. The biggest volume processed to date has been 140 gigabytes. High degree of interactivity is required on these tools, and they have to be easy to use in order for geoscientists to accept them. So we dealt with the pure volume of data we have to process by accelerating our disk-to-disk image processing algorithms with CUDA. We're dealing with these interactivities and ease of use issues by looking at CUDA and GLSL in order to come up with interactive ways of computing. This seismic trace envelope is a very common, very useful seismic attribute. Our multi-threaded processors, going from a single to a quad-core implementation, we've got about 2.4 times speed up with that. As soon as we put on the GPU, we saw order of magnitude, close to 2 order of magnitude increase over a single threaded implementation. But it's generally quad cores that people have on their desks in our industry these days. So realistically, we're looking at about 40 times speed up for this particular algorithm. So a change like this, what does it mean? Well, a typical North Sea data set is 3 to 4, let's say around 4 gigabytes. This algorithm will take more than half an hour to compute on that. This brings it down to seconds. Now that we have all this compute power available, we no longer have to make this black box process that takes a seismic volume and spits out another volume at the end. We can actually make it interactive, make the parameter tuning interactive. So the objective is to go from seismic to something like this. And this is, these are some real geological structures that's been plucked out. The red here is actually what's called a gas chimney, so there's gas moving through the rock there. And because of that, there's likely connections in these blue and yellow areas that need further analysis, but at least we've separated them off. So this is an example of a tool that we put together, a prototype, that uses GLSL and CUDA in order to do multi-attribute classification. So we have a number of attribute volumes, and the user is able to come in and do some mixing in GLSL very quickly. They're able to pan through the data, and they're able to see the contribution and the geometries that come through from the various measurements. This is going to change the way software is used and software is developed, because before this, in order to get to this result, the user would have to generate maybe 10, 15 different volumes on this, look at them, and then go back around and integrate. They can do that all now, on demand. So what's the impact of all this on our software for our users? I'm just going to explain what a typical application of our software is. They'll start off with a seismic reflectivity volume, all those wiggles, and say that's around 10 gigabyte. The working project size needed to achieve that, you can easily have 50 volumes. So that's 500 gigabytes. We're seeing data sizes go up to 100 gigabyte and plus, so you can imagine the storage requirements go up a lot. And those interactive tools can effectively cut this out, because you can do a lot more testing, a lot more quickly. If you look at a 200 kilometer square data set, typical of the North Sea, a project would take 200 weeks to process those, 20 days to process those workflows. If we have that baseline 15% faster volume processing, that drops to 10. And if we assume that we can get an order of magnitude speed up in our faster with the parameter tuning because of the interactive tools, then we've dropped to say a week and a half to complete that project. Most of it being in terms of data I/O and QC. Other projects, typical of offshore Brazil and Africa, are much larger, 70 gigabyte, and the distributions are a bit different there. There's a lot of data loading and data conversion to do. And if we look at the same assumptions, we're seeing that the actual computation time isn't becoming the bottleneck at all now with our tools, and we're able to more than half the timeline for an entire project. All those figures are based on a single GPU implementation, but we're now working on a multi-GPU that will be able to take advantage of the type of boxes that we have on demo next door, and we're commercially releasing those tools next year. Beyond that, we're going to continue this, what I think is a major change in the way that tools should be designed, so that they can deliver computation data on demand for geoscientists, rather than having tools which take a long time to process large data volumes.